Demystifying the partial derivative. All right, let's get right into it. Today, we're breaking down the exact mechanical lever that makes AI optimization actually possible. If you've ever found yourself wondering how on earth a massive neural network actually learns from its mistakes, well, you're in the right place. We are going to unpack the atomic unit of learning itself, the partial derivative. So think about this for a second. When a neural network makes an error, which of its million weights actually caused it? This right here is the fundamental hurdle of machine learning. We call it the attribution problem. Imagine your network outputs a completely wrong prediction. Inside that network, you've got millions, maybe even billions of individual weights. Which specific one caused the error? And honestly, more importantly, how much should we adjust that one specific weight to fix it? If we don't have a mathematically rigorous way to isolate these variables, we are completely flying blind. We'd literally just be tweaking millions of parameters randomly, changing everything all at once and just crossing our fingers. Without a targeted approach, AI would literally be permanently stuck at random guessing. So the absolutely crucial point here is that we need a way to freeze the universe. A standard single variable derivative tells you how fast a car moves when you press the gas pedal. Pretty simple. But the real world and definitely machine learning is multivariable. Historically, physicists hit a massive wall with this. They couldn't just calculate how heat moved through a 3D solid without first asking, wait, changing with respect to which direction? And that's exactly why the partial derivative was developed. It measures the rate of change of a function with respect to one single variable, while rigorously holding all other variables perfectly still. You're basically taking a massive, messy multivariable function and artificially turning it into a single variable one. To really grasp how this feels, let's think about a studio soundboard. Imagine you're mixing a track on a massive board with 50 different sliders. The overall goodness of that song is a function of all 50 of those inputs. If you just push all 50 sliders up simultaneously, which is step one here, sure, the music gets louder, but you have absolutely no idea which slider actually made the mix sound better or worse. It's just chaos. But now look at step two. You lock 49 of those sliders perfectly in place. You tape them down. Then you nudge only the bass slider by just a millimeter. If the mix improves, boom, the partial derivative for the bass is positive. That is the exact human, non-math equivalent of isolating a variable. You nudge one thing, hold everything else constantly in place, and measure the change. But as engineers, we love precision, right? When we transition from a human analogy like that soundboard over to a neural network, we aren't just relying on intuition or listening for a better mix. We don't need to guess. We have a coordinate system. A modern AI model is, at the end of the day, just a massive mathematical function. Training it simply means navigating that coordinate system to minimize a loss function. And you simply cannot navigate if you don't know the exact slope in every single direction. And this is where the visualization gets really cool. Picture a 3D loss surface as a rugged mountain range. To find the partial derivative with respect to x, you're standing on the side of this mountain, but you completely restrict yourself to walk only directly east or west. As your path traces solely in that x direction, look at how the color-coded shadow stays perfectly flat along the y-axis. That shadow is your proof that the north/south direction is completely, 100% frozen. Visually, taking a partial derivative means you are slicing this 3D surface with a vertical plane, laying that slice flat, and just looking at the curve of that one specific, isolated direction. So, to put it plainly, the partial derivative is simply the coordinate-wise slope. It's the exact steepness of the mountain right under your feet, but strictly and exclusively along one axis at a time. This clinical definition right here is what allows a computer to mathematically map the isolated impact of every single parameter on the final error of the entire network. Now pay close attention to the notation. You'll notice we don't use a standard straight D for this. We use the curly D, the partial symbol. And in mathematical notation, this is a massive distinction. A straight D implies a total derivative, where all the variables might be bouncing around and interacting together. The curly D is an explicit, strict rule. It tells anyone reading the math, hey, we are dealing with multiple variables here, but we are artificially and forcefully turning this into a single variable function by treating everything else as a hard constant. Let's actually look at how this plays out with real numbers using finite differences. If we take a tiny, infinitesimal step, let's say an h of 0.001, along just one single axis of our function, we can calculate the approximate slope. In a standard worked equation, taking that tiny 0.001 step gives us a rate of change of 4.002. Now, as that step size shrinks closer and closer to absolute zero, this value perfectly approaches the true analytical derivative of 4. This is the proof. It shows that our isolated little nudge mathematically tracks the exact slope of the function. But actually, here is where we hit a massive computational brick wall. If we actually forced a computer to use that finite difference method, nudging one weight, running the entire network, checking the error, resetting, and repeating, calculating just one single learning step for a 1 billion parameter model would require 1 billion forward passes. That is big O of n squared compute. It is completely, laughably intractable. Enter reverse mode autograd. This requires only big O of n compute, meaning it calculates all the derivatives for all parameters simultaneously in just a single backward pass. It's a total game changer. And this brings us to what we in the field literally call the autograd miracle. During the forward pass, a framework like PyTorch is quietly building a massive computational graph in the background, saving the local derivatives at every single node. Then the real magic happens. Starting from the lost scalar at the very end of the network, it traverses backward using the chain rule. Imagine it. A pulse of light traveling backward from the lost node, flowing down the exact mathematical path to isolate one specific weight out of billions. That pulse of light is the backward gradient. One forward pass, one backward pass, and boom, we have the exact coordinate-wise slope for millions of parameters all at once. So where does this actually live in modern AI architectures? Well, literally everywhere. In a standard linear layer, the partial derivative isolates the exact contribution of a single synaptic connection. In a convolutional neural network, it updates the spatial kernel that detects edges in an image. In transformers, the architecture powering massive LLMs, partial derivatives flow right through the matrix multiplications to perfectly update the query, key, and value projections. And in diffusion models generating AI art, they update the UNet to accurately predict and remove visual noise. The underlying partial derivative math is totally identical across all of them. Now, of course, in the real world, engineers run into pitfalls. Because AutoGrad rigorously relies on that saved computational graph we just talked about, using in-place operations, like modifying a tensor directly with x plus equals 1, will completely break the graph and throw a massive error. Furthermore, we have to deal with the limits of floating point math. If you try to train using float 16 to save some GPU memory, those tiny microscopic partial derivative numbers can easily underflow right to zero, causing vanishing gradients. That's exactly why we use mixed precision, keeping a float 32 master copy of the weight safe to ensure those exact slopes aren't just lost to rounding errors. So what's next? As we look out to the research frontier, we are facing a totally new bottleneck. We know how to find the first-order slope, right? But what about the actual curvature of the loss landscape? Higher-order partial derivatives, like Hessians, would give us absolutely incredible optimization power. But calculating a matrix of partial derivatives for millions of parameters, it requires staggering, almost impossible amounts of memory. It's totally impractical today. So the big open question driving modern optimization research is this: can we somehow approximate the effects of these higher-order partials without actually computing them directly? It is a fascinating problem, and honestly, solving it might just be the very next massive leap in AI efficiency.